If we write an equation for the current in a diode called I sub D is equal to a term called the diode saturation current that I'll call I sub S, and I'll explain this term later. This is times E raised to a power voltage sub D, which is the voltage across the diode, divided by N V sub T minus 1. Now recall that E is a natural logarithm, so E is equal to about 2.718. Now, the N term is between 1 and 2. It's called the quality factor. There are other names for it, but for our typical silicon diode, I think N usually comes out a little closer to 1. Now the V sub T term, V sub T, is called the thermal voltage, and it's equal to KT divided by Q. And K is a Boltzmann's constant. T is the absolute temperature in degrees Kelvin, and Q is the charge on an electron. Now at room temperature, VT is approximately 26 millivolts, or 0.026 volts, and that's at 300 degrees Kelvin, which corresponds to approximate room temperature. Now sometimes it's useful having this equation solve for the diode voltage V sub D. So let's solve for V sub D. Now we can take this equation and divide both sides by I sub S, and when we do that, this will become 1. We can move the 1 over to the other side. So let's rewrite that as I sub diode divided by the saturation current I sub S. And we'll bring the 1 over to this side, and it'll become plus equals to E raised to the V diode divided by N V sub T. Now we can take the natural logarithm Ln of both sides, and we can rearrange the terms a little bit, and we get the voltage across the diode is equal to N V sub T times a natural log of the current in the diode divided by the diode saturation current plus 1. Now let's also repeat the equation for the diode current here. So the diode current is equal to I sub S times E raised to the V sub D divided by NVT minus 1. So let's graph the voltage current relationship of the diode using these equations. So let's plot current in the diode I sub D versus the voltage in the diode V sub D. And for negative voltage, we'll extend our axis this way. So if we look at this E term here, if V sub D is equal to 0, e raised to the 0 power is equal to 1. And if we have 1 minus 1, we get 0 times I sub s, which is 0. So let's change colors here. At this point, the current is equal to 0. And as V sub d is increased in the positive direction, this exponent dominates. This minus 1 becomes negligible. We get a curve that looks something like this. Now, if we make V sub d negative, this exponent term becomes very small. And this minus 1 term dominates. And that minus 1 term is multiplied by the diode saturation current. So we get a very tiny current. It's a little tiny negative current. And eventually the diode will break down, which the breakdown voltage is not modeled in this equation. But this small, very tiny current is the I sub s, or the diode saturation current. That's the current when the diode is reverse biased, and it's very small. In fact, for a small diode on an integrated circuit, I sub s can be approximately 1 times 10 to the minus 18th amps, which is a very small current. And of course, this current will change quite a bit with temperature and with the geometry of the diode, but just a ballpark for a small diode. Give you some feel for how small this current can be. Now let's solve the diode equation for some different current values, and I want to show you something. So let's solve for V sub d is equal to, let's go up here, is equal to NVT, and N for our diode will be approximately 1, and the VT will be 0.026 volts times the natural log of I sub. Let's solve this for a current of 1 milliamp. So our diode current in this case will be 10 to the minus 3 amps, which will be a milliamp. And let's assume the same saturation current of this small diode, which will be 10 to the minus 18th amps. And we have we have a plus 1 term, don't we? Yeah, we have a plus 1 term. That's pretty negligible, but let's include it here. So if we compute the value of this, we'll get a voltage of 0.898 volts. Now if we solve the same equation, instead of a milliamp, let's solve it for 10 times less current, 0.1 milliamp. Now if we do that, we get a V sub d equal to 0.838 volts. Now let's make the current 10 times smaller and solve this equation again. 0.01 milliamps. Now if we solve for V sub d, we get a little smaller number, 0.778 volts. Now notice that the difference in voltage when we change the current by a factor of 10 is 60 millivolts. Now look here. Again, we change the current by a factor of 10, and we get a difference in voltage drop across the diode of 60 millivolts. So there's a rule of thumb. For a decade change in current, the diode voltage changes by 60 millivolts. 60 millivolts. And again, this is per decade. Decade of current change, I'll call it delta I. And this is a rule of thumb that's good to remember. Now there's another rule of thumb. Let's go back to the diode curve. And as the diode temperature increases, this curve, the diode drop, will decrease. And as the temperature increases, actually the saturation current will increase, so it'll become more negative. Now there's a rule of thumb about the voltage drop at a particular current across the diode. And as the temperature increases by 1 degree centigrade, the voltage drop decreases by about 2 millivolts. 2 millivolts per degree centigrade. So this is a good number, or good rule of thumb to remember. So as our temperature increases, the drop across the diode decreases. So this is cold, and this is hot over here. One thing I should point out, the 60 millivolts per decade is the change in drop across the diode. Now diodes will always have a series resistance. It's part of the diode structure, and this is the parasitic resistance that you really can't get rid of. But this 60 millivolts per decade is for the diode part only. It does not include the drop in the parasitic resistance. And that drop will have an effect on the diode curve. If we take this curve here, this yellow curve, and we include the series resistance of the diode, at very small currents it's not very significant. But at higher currents, that resistance drop can become significant, and we can depart from this diode curve, where this drop here, this is a drop across the resistor.